there are 4 codes. We will run them one after another, and it will hopefully make all of us very confident about the class material. So I noticed yesterday that it takes a little discomfort for writing equation of motion for density metrics, and maybe we need well, it should be minimal amount of equations in the lab, but we do need some confidence that density metrics give the same answers as wave function. And the code number 1 will be, which is called like RDM for density metrics, is one way to confirm this thing. So feel free to run it and look into the code, and I will give some comments. Maybe writing a few basic equations. Is code number 2 will confirm that pulse area theorem works, and one can explore it with the in the basis of density metrics, and one can get the same observable images as we did last time with wave function. Code number 3 illustrates what we did today in class to discuss, prove, derive free induction decay, that the length of the block vector gets shorter and shorter and shorter, and we did it by derivation, and in the lab we can prove it in a little more dumb way, just by literally performing average over ensemble and see that this effect is happening. And the number 4 will illustrate the echo effect, just using the same family of the code. I chopped them independently so that each section can be done as a little independent exercise. In the homework, or not homework, lab report, just make a couple of screenshots and a couple of movies, and there are questions at the end that may need to run the codes a few times over again to get some trends. Specifically, here is we are at the learning curve. It's not a big science, but a question that mimics big science. So, question to the code number 3 about decay, about transversal relaxation. So, in the class, we did derive that the time of the decay is inversely proportional to, is like basically 1 over the width of the density of states, where density of states discusses distribution of two-level systems in the ensemble, like the one with smallest energy, the one with largest energy, and their offset dictates how soon or how late the transversal relaxation will happen. If you look onto 1 over T2, inverse of the transversal relaxation, then it should be literally equal to the width of this energy distribution. So a task for the lab report is to check this dependence. So do several runs with different width parameter and see whether it will extend or shorten time, and maybe record it as a table or like a graph. Width of distribution and time of relaxation, or inverse time of relaxation. Does it make sense? Right? Okay. And a little thing at the end is just add a few words about your experience with any echo. Not like shouting in the mountains, but like spin echo, photon echo. If you were never exposed to the experiment, just what you get from just quickly glancing over free sources, so that you make connection between a little bit dry class material and real life. Okay, so let's, and please, if you feel comfortable with the if you feel comfortable with these codes and their explanation, do not wait for me. Just run them and feel yourself free. I'm going to do a little exercise for myself, but I hope you will benefit from it as well before we start. So if you do have one, by the way, in the recent quiz, that's like 3 or 4 class submitted, and the rest decided to do at home. Out of 4, 1 was attentive, and another 3 were following visual patterns. So I was not intending to make traps. It was just so in the quiz they were arranged this way. So populations first, coherences second, and in the class we were considering population first and last in the symmetric form of this super operator that you can memorize visually relates to what we did in class. In the quiz, only one of the class attendees followed what is the content of the matrix and elements, and the rest just tried to reproduce the shape of the matrix, which is okay. We are on the learning curve. And 2, row 2, 1, row 1, 1, row 2, 2, row 1, 2, row 2, 1. So if I do not count on my memory, how do I feel these elements? Well, if I do count on the memory, it should be omega Rabi in this edges, right? Plus delta minus a delta there, and some factors like h bars and minus 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 minus, and the rest is easy, right? So it's the best I can remember from the top of the head. But I will fail to do a closed book exam, or I will need more time for derivations. And zeros in here. Does it agree with your vision of this? Right? Approximately remembering something. So how can I get this matrix if I'm under pressure and I do not have like cheat sheet and books with me? I just didn't find a place in the lecture material to put it, but who remembers Heisenberg equation of motion? Or something like, okay, who has no idea or extreme hate feeling to Heisenberg equations of motion? Like, who doesn't care about Heisenberg equations of motion? Who is very optimistic and knows what Heisenberg equations of motion are? Just show something. It's not for the grade. It's for me too. Okay. So the I also would need probably to trim, because I always forget the sign here. I can easily flip it. So if you have it in some open sources, you can
positive by raise bar.
Okay, so no minus, and A goes first.
Commutator is the other way around. So how you have it written.
So in this way, it should be minus. Okay.
That's theorem, or is that?
Ehrenfest theorem is a particular case of Heisenberg equation of motion.
Okay.
So this is very general, and Ehrenfest is only for position and momentum. Okay. So it's from like basic quantum theory. If we need to help experimental colleagues and predict some observables, we always can get it by doing bra and cat with wave function that we find and operator of an observable. But computing wave function for multidimensional systems is always a challenge. At the time when there were no computers, there was a shortcut offered by Heisenberg is to derive equations of motion, not for wave function and then finding the convolution, but directly for the observable, or more rigorously, directly for the operator that controls the observable. And this notation of brackets is flipping the order commutation, so it's Haha equation, right? Oh, what do you think about Heisenberg equation of motion? Do you like it or do you hate it? We don't care. Okay, you are in the majority group. So, density metrics are elements, are kind of expansion coefficients for the density operator. So we replace expansion coefficients in our practical approaches by the elements of density metrics, which are pairs of expansion coefficients with one of them is conjugated, right? But one can speak not about these elements which are typically written in form of matrix. But one can combine them with cat times bra with dyadic products of the basis vectors and compose an operator, right? So no one objects, even if okay. Now I'm going to erase it because you leave it. So if this is correct, it means that ddt rho mu minus IH bar rho H, right? And if we explore matrix elements of this equation, for example, we put bra and cat, 1 and 1 for each element, or 1 and 2, or 2 and 2, explore all possible values, then this equation will be written in the matrix form, will be written in the following way: d dt rho 1 1 rho 2 2 rho 1 2 rho 2 1 equals 2 minus I h bar rho 1 1 rho 2 2 rho 1 2 rho 2 1 matrix elements of Hamiltonian 1 1 2 2 1 2 2 1 minus rho 1 1 2 2 1 2 1 2 2 1 1, and once again rho 1 1 rho 2 2 rho 1 2 rho 2 1. My plan was to make all derivations and plug in all elements here, but I'm lazy to walk there, so probably a derivation when needed redraw this matrix and fill it. So rho by column, right? Rho by column. Yes, I h bar rho 1 1 h 1 1 plus rho 1 2 h 1. Rho by column, row 1, 1, H1, 2, plus row 1, 2, H2, 2. Row by column, row 2, 1, H1, 1, plus row 2, 2, H2, 1. Row by column, row 2, 1, H1, 2, plus row 2, 2, H2, 2. This matrix and subtract minus I which bar, and then repeat this exercise for this second matrix. H11 row 1, 1 plus H12 row 1, 2. H11 row 1, 2 plus H12 row 2, 2. Row by column H21 row 1, 1 plus H22 row 2, 1. And the last one H12 row 1, 2 plus H22 row 2, 2. So do we see anything will cancel? So if we subtract, I do see that this one in the last element will cancel, right? This one will cancel. This will not. Now let's explore here. 1, 1, 1, 2. And this is so this and this will cancel. And let's look on to lower left. H21 row. No, nothing. Nothing is canceling. Nothing is canceling here. Let me double check if I was correct in the upper right. No, this is not. This doesn't cancel. So I already started this, so I will complete. But the plan of this video derivation is to show that if I complete this writing down and then expand it into the matrix 4 by 4 and plug in the values for H12 equals Rabi and H11 plus delta over 2 H22 minus delta over 2. We will construct the matrix that we were deriving 2 classes ago and that we were trying to memorize yesterday in the classes. This definition of the equation of motion for the density matrix is more standard. It just looks maybe a little quicker but less elegant. When we do by hand time derivative of wave function, it may sound a little bit more convincing. Okay, so I'll probably will erase upper part and then continue this exploration. So we do have row 1, 2, H21. H21 minus H12. So 25% done. Next one. Row 1 minus row 2 times H12. So I noticed this one and this one. Then the next row 1, 2, H22 minus H11. So 50% done. And you see that elements of Hamiltonian come in pairs, and like delta over 2 and radius over 2 will come in pairs and will either cancel each other or plus 1/2 will be 1, right? You can do it. Okay, so let's complete this journey. Row 2, 1, H11 minus H22. So it was this element and this element. And then here plus H21 row 2 minus row 1. Okay. %75% done. And the last one. This one under the question. So I do have a little doubt about this term, but the rest of the terms seem correct. Do you follow, or you are completely hating and or do not caring? Do you follow the idea? I don't know, maybe it's a good occasion, or maybe it is a truth. When I ask, do you really hate this material? Okay, and now my task is to unroll this expression into the matrix 4×4. So let's start from time derivative of rho and 1. It is getting contributions. If I didn't make an error from, yes, I think I did an error. H bar, and then rho to 1 is minus H12. There, according to what we derived here, there are no contributions from population terms. Right? Now let's look for contributions to the first of the coherences. So it is contributed by first population with positive sign and with H12. It is contributed by the population of the excited state with negative sign H12. By now, you see all of those will be Rabi frequencies, right? So the change of this coherency will be contributed by itself proportional to the subtraction of the excited state energy minus ground state energy. No. And there is no contribution from another coherency. Right? So let's explore how it will be contributed for the second coherency. So rho to 1 is contributed by itself times subtraction of the diagonal Hamiltonian, but see they come in the different order. One can put minus sign here and put again 2 H22 minus H11. So signs here and there are different, right? So next, it is contributed by the population of the excited state with plus H21, and is contributed by population of the ground state with minus H21. And no contribution from the different coherencies. Okay, 75% done. Now the last one. How does the time derivative of the excited state population depends on other elements? So it is not contributed by itself or another population. It does depend on coherency 1, 2 with minus H1, and it does depend on the coherency to 1 with plus H12. Does anyone care about what is written here, or anyone wants to object? So do you see it repeats the visual pattern that we derived together a week ago and tried to reproduce a day ago? So we do have minus in upper right and lower left. We do have pluses in upper left and lower right. We do have anti-diagonal zero, and we do have energy delta over 2 minus delta over 2, which will be delta, the energy offset between spin up, spin down, or grounded excited state. And here will be the same thing with minus sign. Okay. So it is what I would be doing if a ship or airplane crashes. I'm thrown on the inhabited island, and suddenly I decided I need an equation of motion for density matrix. So we can derive it, right? And then replace this by delta, this by radial frequency. Okay. I'm very happy and comfortable. So if you, I don't remember if you designed any, well, those of you who didn't submit a quiz will try to put this thing there. And then you all get a certificate of experts in density matrix equation motion. Okay. Let's stop this one and start sharing. So let's start from running the first code, just RDM. And did you run it? Please raise hands if you did, or show down if you didn't. Who didn't?
I don't do it right.
Well, did you run the codes from email? So please try to download them. So as you may see, it shows the same sequence of pulses, right? And it shows the populations of row 1, row 2, and then row 1, 2, imaginary part. So if the pulses are arranged to have the pulse area pi, they just inverse population. So this code is useless. If you look on the outcome, we were already grown enough to get the same results with a wave function a week ago, right? But we may want to look inside the code and check if we need to work how to erase it. How it correlates to what is written in the code itself. Can we? So what is going on? So the setup of the parameters is borrowed. It is the same. but instead of propagating wave function, it works in the representation of Liouville equation of motion. So instead of defining Hamiltonian 2 by 2, we define Liouville operator 4 by 4. And you see there is a like offset with plus, offset with minus, and then the pattern of radio frequency with minuses in upper right and lower left, and then pluses in the upper left and lower right, while the main like the anti-diagonal as zeros. If you did look on the printout from book of Shaul Mukamal, you may have noticed that he did make an attempt to make a full analogy between any quantum operations one does in quantum mechanics with wave functions and quantum mechanics with Liouville operator. I borrow it for a minute. So overview. Share. It may not come into the recordings, but who cares about the recordings? It's more important that we see it together. So if one practices equation of motion for wave function, derivative is governed by the Hamiltonian. If one needs to look for evolution, then the evolution operator is not here. There. Evolution operator is exponential of the Hamiltonian. Exponential of the Hamiltonian, right? So if we are in the basis of density matrix, or as Shaul Mukamal tells in the basis of in Liouville space, then he moves minus I over h bar away from the Liouville operators. Like in our notation, we kept it there, but it's a question of factor. But then it looks very much in the same way, right? Imaginary unit, Planck constant, and then Liouville operator. But this rho is not a wave function, but it is this dyadic thing for density operator. Then if one needs the propagating forwards in time, one also can design an evolution operator, right? And he uses this instead of regular U, he uses calligraphic U, right? And then if one needs an analog of evolution operator, he just places exponential into the power of Liouville operator. So it's everything is the same, or everything is the same by the formula, right? Okay. And I think this little exploration will be not seen in the recording, but since you all have this printouts, you will be able to look on it. And there will be, on recording, there will be no evidences of violating copyright. Okay. So if I want to be an obedient pupil of Dr. Mukamal, I need to put minus I over h bar away from these brackets. But if I just need to run something, design a code that works, who cares where it is? Now, we can tell that here is the evolution operator, right, in Liouville space. And if it applies to density matrix of the past, it will give us density matrix of the future. So same as in our previous life, in our previous career, we were practicing evolution operator in the basis of wave function. Now we practice evolution operator in the basis of density operator, right? So we only need to define what was the density operator as the initial point of trajectory. And we can define it as this rho naught, and we can set it to be ground state is populated by 100%, excited state is populated by 0%, and coherence is 0. So we are sitting on the south pole. Right? And then the parameters here are identical to previous versions of the code. If you do evolution over many, we are still in the interaction representation. Therefore, we do not have quick accumulation of phase. We have only this offset, right? And this offset is very near 0. Let's locate where it is. So we set it to be very close to the frequency. We have frequency, we have transition energy of the system, and we select offset to be like 1/1000 of this value, just to be not in a perfect. I learned it from London. So Patricia wrote in the paper ideal resonance, and London made a verbal collection. It's not ideal; it's perfect resonance. If you looked on the corrections and recordings, okay. And then we just accumulate, we form evolution, so variable TT accumulates present and value of time, which uses d tau, right? And we already discovered if we are in the interaction picture or rotating frame, size of this time increment is not as important. We have quite flexible freedom to have it small or big if we do not have quick oscillations. So TT is accumulated time. Here we have several pulses which come to close to each other. Later on in the second code, if I want to, right now parameters are set up to pi pulse. If I want to make a twice smaller area, I can just change this factor, right? But right now I do not need it. And then we add together this value of the field at a given time, accumulate the value of the field to show this quick oscillations, and just propagate. As soon as we, and then we accumulate values of all elements of rho. If you would prefer to write down density matrix as a matrix and make a snapshot at each time, we will come. It's all doable, all possible, but it creates a little discomfort. Matrix has 2 indices and time is a third index, so it means you need a 3-dimensional tensor, 3-dimensional array, which is okay, especially if you program in Perl or Fortran. But if you use pre-made libraries for matrices, they do not have objects for like multiplication and storage of the 3-dimensional vectors, or they are not as quick. So it's the whole business of storing density operator in a vector is just to use precompiled libraries that process vectors and matrices. So it's not a big science, it's just a convenient way to save information. And then we can, if you have snapshots of this dynamics, we can use this vector accumulated in the array with more and more columns, like matrices or whatever. I can double check this 4 by 6,000 array, which accumulates snapshots of the density matrix. And then as soon as the dynamics is done, one can simply plot element number 1, which will be population, element number 2 is your excited state population, and then we need to imagine the part because in absence of relaxation, and I think even in relaxation, off-diagonal elements are imaginary. And this property that populations are real and coherences are imaginary, it is the reason why so there is additional restriction that allows to project two complex numbers, which means 4 independent variables onto surface of a sphere, which is basically 2 independent variables. Okay, and this one is just the oscillating field which induces transitions. So by running this code, one is getting pi pulses, exciting and then de-exciting. Any questions, suggestions about this part? No? Yes, please.
I'm kind of confused by the coherence, the transitions. Like when I imagine what transitions talk about, I was thinking that it's the process in which the moving from like the ground state to the excited state. I am still trying to understand the concept of it creating its own pathway. Like if there's no pathway already, like it's not moving from the ground state to
That's great. Patricia is a champion of asking the right questions, objectively. Let me offer you a little thought that you may eventually like. So I'm not declaring that I'm giving answer or right answer to the question, but I'm just offering direction thought that may make you happy. So imagine that you take, let's say, red line and take derivative over time. So when red line is not changing over time, the derivative is 0. When it is changing over time, the derivative is 0. When it is experiencing a sharp transition, the derivative is maximum. So when there is a transition between states, derivative of population is maximum. Can you live with this? And just by equations, derivative of population is coherency. So, so by telling that coherency signifies that the transition is happening, it's nothing by telling that there is a non-zero derivative of population. Okay? It's a perfect question. I remember myself asking this question to myself and feeling confused. Okay. Okay. Did everyone run this? Lola, did you run this code? Okay. Now let's go to the next code. Pulse. So I will open the code, do a little modification, run another time, and then do a discussion. So this. And save. And run. Okay, so it is something that we all are happy or almost happy to observe, right? So pi pulse converts system from ground to excited state. and the coherences are non-zero only during the this transition, and then they come back to zero. So this version of the code, to have the correct title, I edited the last two lines, so it's just manipulating. It's not science, it's labeling. And then in the line that defines, originally it was trains of pulses, but now we have only one pulse. So you see the definition of cycle over several delayed pulses is commented out, and there is a same arrangement of pulses as we used before, and we agreed that they are pulses. And the rest is the same. We are still in the Liouville time evolution density matrix. Now, if I want to have pi over 2, it means I need to lower the area of the pulse. If I'm in the middle school, I'm doing some basic geometry, and I have an assignment to, like, I have a rectangle, and I need to build a rectangle that has an area 2 times smaller. I can either change its width or change its height. So if I change the height 2 times, the area will be 2 times smaller. If it originally area was equal to pi, I make it 2 times smaller, it will be pi over 2. So the name denominator is a little deceptive. It's not denominator, it's factor, right? But I introduced this height twice smaller. I anticipate that it will be pi over 2, save, and run. Yeah, if you don't mind. All right, we like to share your observations. Just anything you can comment about this figure.
Heard to the first one. Still has
The one for pi over 2. Yeah.
Yeah.
So what happens to populations, to the orange and blue?
The ground state decreases while the excited state increases, but they kind of, as time goes on, stop once they hit
Okay.
about half the population.
Excellent. Yeah, thank you. Question because you were asking previous question. What happens to coherences? The dashed lines.
What happens to them? They increase. And when they go to the place where the population of the excited state and ground state is the same, then stop. Yes, stop changing.
Okay, yeah, thank you. So you see it, the up to like end of the pulse, it goes the same way as before. When the population is changing, coherences are raising and identifying that there are transitions. But then, if the populations will stop raising in a little sharper way, the coherence would decline and go to 0. But it kind of stops in the middle. Therefore, coherence stops changing, and it stays where we left it. Right? And it's not coherence, it's the imaginary part of coherence. We, as humans, we do not see in the imaginary plane. So these dashed lines are row 1, row 1, 2, row 2, 1, and they are not absolutely steady because we did set up a little offset. If the offset will be 0, they will be flat. Since there is a little offset, it will be very, very slow oscillation. They will cross x-axis and then slopes and then form very slow full oscillations with amplitude 0.5.
Next, the offset is not, I'm just trying to like, what is the offset you're trying to talk about? Like, is it that they are not like they're not in resonance? Is that what you're trying to say?
Yeah, how far we are from the resonance? How important is resonance if you accept verbal formula of London? So we can do a little experiment that we didn't plan. Let's do it minus save and see what what would happen if you rerun. Basically nothing, but if you put it absolute zero, save. So you see, it doesn't change anymore. If we and we will utilize it further. If we make it instead of 1/1000, we'll make it 1%. Save. Run. So it will be oscillating. Make sense? Okay, thank you. What does this correspond to? How can we imagine it? I think we were discussing it before, but anyone wants to say which trajectory on the surface of the block sphere would it correspond to? If Z projection and population of the excited minus population of ground is will be as Z divided by 2. So how if the Z projection changes from -1/2 to 0, and X and Y projections change to their Y gets to maximum and X doesn't change, what would it correspond to? So as Z changes from 0 to pi/2, as X is not changing, and as Y changes from 0 to pi/2. Like, just draw a trajectory. You started at South Pole, then or whatever. If you start from North Pole or from South Pole, where are you ending up? Huh?
At the equator.
Perfect, absolutely correct. Everyone agrees? So halfway north of South Pole. Okay, great. Any questions about or any discomfort? Don't hesitate. If you have a brain.
This yellow dashed line is no longer derivative. It's something different.
When it was derivative here, well, it is literal definition of this dashed line. It's the off diagonal element of the density matrix. Okay, that are based equation of motion for density matrix that no one was objecting against. Even if you do not believe it, but it is still on the board. Okay. I find this everything. So do I have your permission to go to the code number 3? Yes, no, some.
Sorry, someone asked, like, I'm curious why matrix solutions instead of the wave functions. Like,
Patricia confirms her reputation as a champion of questions. Did you hear her question? Did everyone hear her question? This, in some sense, one can tell that it is the main question of the whole course. So, why rho? Why not psi? Or why Dr. Mukamal wrote his book? Up to, and the timing is perfect because the next code would answer this question. But is there a reason why wave function is not sufficient to describe the whole range of the natural phenomena? Or which nature of phenomena or states of the systems are not possible to describe with wave function? Do I reproduce your logic? So, do you remember the presentation by Max last time? Which was strategically perfectly arranged, but there were some things that need a little bit of fine-tuning. Do you remember what Max was presenting? Max, do you remember what you were presenting? I think everyone forgot. Except us.
The difference between pure and mixed states. So pure states is what we think of with wave function, where it's just a few systems, and mixed states is when we have a lot of energy levels. And so to go from that, we have to use the density matrix. So we can start working with partition function and ensembles.
Okay, yeah, thank you. So I believe all of us have been exposed to statistical thermodynamics to one or another extent. At least all of us did heard about it. We do not need to love it. We may hate it, but we've heard about its existence. And statistical thermodynamics often neglects all our baggage of quantum theory. It just tells about probabilities and at most populations, right? It tells like everything is under Boltzmann distribution. Probability that system is in excited state is just minus energy over kT, right? So it tells about populations. And wave function also tells about populations. But if you have expansion coefficient of wave function, we need to take expansion coefficient absolute value squared to get population, right? So if we need to make an analogy with Boltzmann factor and apply statistical thermodynamics apparatus, we need to speak on the language of C sub I absolute value squared. If we speak about C sub I without square, then, I don't know, we may need to take a square root of Boltzmann distribution, which by some reason no one introduced. And statistical thermodynamics never tells about transitions between ground and excited. It tells only about equilibrium. It doesn't tell about non-equilibrium phenomena. So on one hand, we to make connection between statistical thermodynamics and quantum, we need something that is proportional to wave function squared by dimensionality. And on another, we need to find a way to combine transitional phenomena or non-equilibrium processes with apparatus of statistical thermodynamics. Wave function is an object that misses populations. We need to do an operation to get the population. We need to take absolute value squared, and then it will be only part of information. If you rigorously make all possible pairs of expansion coefficients with conjugation, it will be more elements than elements in the wave function, and then we naturally arrive to density matrix. What else? Pure and statistical mixtures. fact that statistical thermodynamics doesn't talk about transitions. It talks about like ground and degree of excitation. Means it assumes that all transitions have disappeared. All transitions have happened and stopped by the time we describe the system. We do measurement or description. So if we already know a little bit about density, it means that no matter what, we arrive to such situation when these coherences did arrive to zero. If we do pure state, meaning we practice only quantum mechanics, there is, if we assume isolated system, there is no mechanism in quantum mechanics to describe a state which is 50% populated but has no coherency, right? 50% populated and no coherency would correspond to zero length of the Bloch vector. And it is not possible in pure quantum mechanics, right? So density matrix is mandatory, is needed to describe transition of system from pure to equilibrium. So if you need pure states, we can use quantum mechanics. If we use equilibrium, we can use statistical thermodynamics. And density matrix is needed to describe transition from pure to equilibrium. Okay. Statistical thermo, like population E minus delta E KT, quantum CI CJ, CI CI population, C star ICJ transitions. So if we want a transition from quantum to statistical, we do need density matrix. So we need transition from pure to equilibrium. Does it address the question? Okay, thank you. Do I have a permission to go to the next piece of code? Okay, yeah, thank you. Next one is decay. So you see it scans through several elements of ensemble. And it creates, I noticed that most of you have already run all 4 codes, and I'm just playing a role of entertainer. Patricia and Story and Max were already speaking. Let's question, what do you see on this view? Fair enough. Indeed, why? See once again. Thank you. So you've got 20 seconds to think now. What is your interpretation of what you see there and what you will see in yours? Just tell me what you observe.
Purple, dash lines or something like that.
Mm-hmm.
The purple dash lines, what does it represent?
Of diagonal multiplication. Like number of lines, is it the same as in previous code or it's a little bit bigger, larger?
No, it's larger.
Okay, if you do visual connection between previous code and this one, would you tell that it is likely 5 pulse or 5 or 2 pulse?
This looks like a 5-pulse.
Or 5 or 2?
This is a 5-pulse.
No, it's hard. Populations, the blue population goes from 1 to 50%. Right?
I thought the previous one was 5/2.
Previous one was 5 or 2 and this was 5.
Oh,
Okay, Adam, what do you think?
Yeah, 5/2, for sure.
That was
Consistent. Well, I noticed that it was going through pieces called ensemble, and there are 40 of them. There are like 20 of these yellow trajectories and 20 of these purple ones. It looks like. You mentioned, I think, before that this dashed line is the average for each of those. But I guess it just looks at
okay.
a bunch of different values for those off diagonal.
Okay, good enough. That's I'm going to question. So, what is this purple and yellow lines and how they connect to oscillations of frequencies and all this one? The figure of set.
Okay, for what I can tell in the code. What the ensemble relates to or these different lines correspond to different offsets. So-
Yes, excellent, excellent. It is what I wanted to hear. Yeah, and they give different frequencies of oscillations. I know that David and London didn't have questions, but we answered everything we needed. Maybe there will be questions from the next code. So if we this corresponds to pi pulse because it gives 50% excitation of excited state and 50% change of the ground, right? Since there are slightly different parameters, line becomes thicker because it is adding to overlaying several electronic state trajectories. Now, different trajectories have slightly different offset between system and the electromagnetic radiation frequency, which can correspond to the situation when in the solvent there are different local environment, like dipole molecules in the environment are rotated towards or outwards of the molecule, and they slightly differently polarize our object of interest. So there is a distribution of frequencies. And for each of the elements of ensemble, we have slightly different offset, which means upon creating, as Tori taught us, after we come to the equator, right? Each of these travelers start running along the equator, right? But they have different paces. So the quickest one, like cosine, quickest one goes around the equator quick. The slowest one almost stay on the places. And some of them are immediately go in the opposite direction. So it's very broad distribution. So like someone walks clockwise, some are quicker, some are slower, right? And then we can perform at each point of time, we add together value of all of these 40 trajectories. They are, it looks like 20 because we have clockwise and counterclockwise. They just overlay. But we add all of them together, and in the mean of this distribution, we have an average line. So dashes is a mean line of this swirl of trajectories for row 1, 2, and this dot dashes is an average of the zero of trajectories of row 2, 1. And each of the individual trajectories objectively performs unitary Hamiltonian oscillations. They will come to the same place. But if we make an average over them, they come to zero, then they slightly increase, but then this amplitude will decrease and decrease and decrease. If one takes more realistic average, it will, instead of this sinc function, sine over sine delta times t over t, right? Instead of sinc function, it will be just exponentially decaying. When one does see on the experiment. I do see a question in the isotory. No? Okay. So I did try to modify this code that you see after counting 40, it stops and pause and press any key. It may delay, I didn't attempt to convert this simulation into movie, but let's see how it goes. It may take too long time. So, better run it at home. Like set it up at midnight and look at the results in the morning. What probably instead of showing this simulation, I did an upload. And also I did share it with everyone. So there should be, yeah. You see, by some reason here it starts with North Pole, but then goes by over 2 pulses, it arrives to equator, and then the average, instead of running left or right, it goes toward the center. It's like a little dwarf making a seal. And right now it will stop in the middle because I lost the patience. Oh, no, this one works as well. So maybe a little patience will result in.
Slower and slower the longer.
Yeah, I would not brag as a most optimal code or like competing for an elegant coding award. It accumulates more and more graphical objects on the same like 2,000 little circles, and they overlay, which is not good. But it gives like a picture. So let's look how it was programmed so that we can see any benefits for our class. So decay. And I believe it was the most non-trivial creative question in the web report. So initial state is the same. If I scroll to the center, the Liouville operator is the same. The evolution is the same. But loop over time steps. But if you go over, you see another cycle, and cycle over an ensemble. And then we do statistical density metrics here. So we add together density matrices for several elements of an ensemble. I'll do a comment on the board a little later. So if you scroll at the error, so it goes for ensemble to an ensemble, number of ensemble. And it writes down in the command line how far we are down to this. So the offset is automatically programmed to change from minus d/2 to energy step times number of ensemble. So I believe it will be from minus d/2 to plus d/2 for total number, right? So the parameters that everyone is invited to change at home is this one. So change this parameter and see how the code develops quicker or slower relaxation. So what one may expect, so that if one takes broader or narrower ensemble, the point when the coherence declines to 0 will occur earlier or later. And if the derivations of that we did in the class were correct, then 1 over T2, 1 over this time when it intersects, will be linearly depending with this parameter of what was the name of the code? Disorder. So if you write the if you plot value of disorder on X and 1 divided by time where in the dash line intersects x-axis on y, it should be a linear function, or several dots that can be connected by a line. But by now, I haven't made this experiment. Maybe I will do it myself by the time of the next lab to have an answer key to check what you are doing. But it is very much expected to have a linear dependence. So we have a little grain of science, of clinical experiment in what we do here. Okay, further back to the code. So in each element of ensemble, we do set value of the offset, and it is different each time, right? We record value of offset just in case it will be needed later. Then we do dynamics over time and accumulate the electronic trajectory elements of density matrix in overall. And then we do statistical average. So this line is, in some sense, an answer to, or continuation of the answer to Patricia. So we take into account the fact that we model not one quantum system, but ensemble, like Avogadro number or like 40 quantum systems, and we find their average property. So we tell that we did have density matrix for element of an ensemble, and now we do summation over all elements of an ensemble, and it will be average density matrix. So this operation, averaging over ensemble, is not possible in terms of wave function. It's for wave function is ill-defined because they're complex numbers. They're not designed for averaging ensemble. They designed only for oscillations. They do not have relaxation. They do not have procedure for ensemble, and it is what was not in a right detailed explanation in the previous talk by Max. So you excellently presented necessity to combine quantum and statistical representation, but then it was an attempt to put like Boltzmann distribution directly into wave function, which Patricia will not allow us to do from now on. And it's absolutely natural that this transition was missing, because it is what we do in this class is away from quantum theory class and is away from statistical thermodynamics. It's something different. It's a way to, it's an attempt to bridge them together. And the bridge from statistical thermo and quantum is density metrics. So it is very fundamental universal concept. And it is, this is what we do in this code. Right. So as we see in the movie, or snapshot of the movie, it's still going on. So for the first part of trajectory, although it is an average over ensemble, it reproduces the trajectory that can be obtained by regular means of quantum mechanics, right? Moving from North Pole to equator. But then good deeds of small dwarfs is not possible. Quantum mechanics doesn't allow this procedure. What we do here, we violate postulates of quantum mechanics, because it tells that systems stay in ground state or have superpositions between eigenstate. This is not a superposition, because it is a summation over several quantum systems. And here, this little circle shows the lengths of the Bloch vector of pseudospin. So in average, it comes to 0, which is very against. It's a big violation of quantum mechanics, but it is quite natural in all experiment, because we add together. So density metrics sets a bridge between stat thermo and quantum. Let's see if you missed anything else in the code. So a little thing which doesn't bring any new science, but makes our hands clean. If we want to perform this averaging, we need normalization. And the healthy way is just divide by, add together number one as many times as many elements in the ensemble. And if you do this, then we do good practice. Otherwise, it could be some there is a sarcastic word for bad results, but it's sarcastic but polite. Artifact. So if you do not do normalization, there could be artifacts in the observables. So we divide by count, and then statistical row element 1 and statistical row element 4 are populations, and then imaginary of statistical row is row 1, 2. Imaginary of statistical row 3 is row 2, 1. And they show this decline. So at this point, one is done, and then one can also convert these elements of density metrics into projections of average projections of pseudospin that we were discussing in class, right? By adding and subtracting diagonal and off-diagonal elements. Total number of adding and subtractions is 4, but adding populations will give 1, so it's trivial. Therefore, we have only 3 things for spin. And then after pause, it does standard things of setting up the stream where to save, and then it plots elements of the spin projections at certain time point. And then makes a screenshot and saves it into a file. After it is done, it does one more thing that I want to focus your attention at. Yes, now it shows pause, press any key. And we are going to get. No? Okay, I can do it just by hand. So this little combination, I really wanted to attract your attention because it's a way to summarize results of simulation in a very simple and the way that avoids unnecessary details but catches everything. So if we add together statistically averaged projections of spin, statistically averaged and squares of the projections of spin, x squared, y squared, z squared, we can have radius that goes to 0. If v goes to 0 and then slightly oscillates and then completely goes to 0. We do know that after pulse is over, nothing happens with the population. Basically, it's 0. So one can just add together x and y projections. So if if the amount of elements of ensemble with positive detuning and negative detuning will be not equal, then Sx and Sy would perform a spiral. Since they are equal and clockwise and counterclockwise motion compensate each other, it just asymptotically digs hole towards the center of the globe. But you can make an experiment and make an offset on offset. So it will be unsymmetric, and then you will observe spiral motion. Any questions, concerns about code number 3? Or just counting minutes until we are done, because everyone is so exhausted. Okay, so let's go to the code number 3. Number 4, sorry. So command window, clear. I will erase this figures. So the last code is echo. So it also screens through several elements of an ensemble. Probably the same number. Big wonder, they originate from each other. Okay. David and London were not questions today. No question today. So kids in the kindergarten, just what do you see?
Looks like we're doing 2 pulses.
Okay.
And we're getting to full population inversion in at least one of the cases.
Okay. Is there any similarities between this figure and the outcome of the previous code?
Looks like basically the same thing as the previous code, except like before the second pulse, it's the same as the previous code.
Perfect. Yeah, thank you. So until the second pulse, it is basically reproduce everything we had before. Do you see? Okay. So, David, any comments? What is the area of the second pulse? Just visually, is it the same as the first or something different?
Looks about the same, might be slightly bigger, thicker.
Slightly thicker, previous one, 502, this one could be. I just think it might.
It doesn't bother me, but I just, yeah.
Okay, so what happens to the dashed lines that corresponds to this?
They make a quick offset at the pulse point. That makes sense.
So, can you say that the instant where the second pulse comes is like a mirror, and if you move, it's like a mirror reflection?
Yeah, so they
Symmetric.
symmetric, yeah. It's going opposite the way they were before.
Okay, in the previous run, we had this oscillating lines declining to zero. What happens to them in this case?
They start going back up.
Okay, yeah. That's all.
Away from zero.
I wanted to hear. So, and if you look on the individual trajectories, so they here they are completely dephased. So they at a time when the average coherency is zero, it means some of the runners are on the left of the stadium, some on the right, and in average position of a runner of a stadium is on a center, right? Which doesn't make sense. Each of them is on the circle, but in average is in the center. But after they are set to run backwards, we wait certain time, and then they come back. Well, not ideally to the same, but to the opposite. But they have the same. They meet each other at the same point. So when they are completely off phase, one can call it dephasing. When they came together, it's rephasing. So population, it has some contribution to get like there is a distribution, but in average population stays 1/2, right? Both ground and excited. And population is not as important. It is more important to have off-diagonal elements that corresponds to transitions, that corresponds to SX and SY. And there is a question that Patricia may have asked a minute ago. At least there is a question that I was asking myself in the same circumstances when I was on the other side of a barrier. Why people do not care about population? Why people care so much about rephasing of coherences? I do not have clear words, but I can share thoughts. So we did identify that there is some connection between coherences and either transitions or ability to perform transitions. On one hand. On another hand, if we would try to find expectation value of transition dipole, if it is optical spectroscopy, they will depend only on the off-diagonal elements of density matrix. So when system has off-diagonal elements of density matrix non-zero, it means system has potential, it is polarized and is able to immediately participate in either emission of or absorption of light. If we speak about radio frequency NMR, this transversal components, SX, SY, transversal to the main magnet, means that when they are moving, it's oscillatory electromagnetic field that absorbs or emits radio waves. So coherency, SX, SY projections are in some way connected to processes of transition, to ability to emit or absorb electromagnetic radiation. When in average, when their value in average is 0, it means system becomes transparent for incident light and transparent as an emitter. But when they rephase, it means it flashes back. They come together. If one would introduce connection between them, they may, as David taught us, they may introduce facilitates not spontaneous, the stimulated emission. So if all of them came in the same phase, and even one of them emitted a photon, it immediately comes to the same phase to all neighbors, and it will be an avalanche of emitting everywhere. So I do not have a clear, mathematically correct short verbal motion, but there is a sense that rephasing of these off-diagonal elements is naturally connected to ability to absorb, emit, and interact with outside radiation. Okay, we are almost over time. Let's quickly glance over the script and then depart in peace. Photon echo. So if I never participated in writing these codes and will be only sitting here and listening what happened, I would assume that code number 4 is a derivative of code number 3, so it should have the same structure. But the only thing that London and David noticed for us that the code number 4 has 2 pulses. So the part of the code that introduces the pulse in variable f should be different. Let's see. So pulse 1, denominator over 2, so it will be pi pulse. And then the second pulse denominator is not variable genome, is not modified. And let's see at which time they happen. So first pulse happens close to 0. The offset, so this is pulse is what is used as a center of the Gaussian function. Where we center the pulse in time. And second one is offset by 1.5 of this unit. So it is of the radio frequency. So it's offset away from the center. The rest is the same. So we use evolution, we accumulate statistical row, we convert it into, we plot it, and then we convert it into projections of SZ. And there is a unit that makes a movie. Right? We don't have time to run the movie ourselves, but we can look on how it performs. In the recordings. So for the beginning, it reproduces what we had for the free induction decay. So it arrives to the equator. Then it dumps to the center of the globe. And then suddenly it starts, it makes some, it waits a little bit there. Waits. And then my patience expired before it came back. But this trajectory shows that it rephases on the opposite side. So it comes, it's like a silo that helps to go from the center of the planet back to the surface. And it corresponds that it rephases and becomes available for absorbing and emitting. Any questions? Is it Any objections? Is there enough information to write a little report? Yes. I hate reports. So, I'm to smile too. So meeting is done. Thank you much for investing your time. And I know we are living on a very tough schedule and I'm responsible for making your schedule tougher, but to go along the schedule, I would really appreciate if you sent your slides tonight. If everything goes as planned, there will be 2